Hello everyone. This time the case history is the Eurotunnel, the tunnel between France and England. That was drilled 2.5 decades ago, and then we'll talk about volume, weight relationships, and try to do a few problems associated with this. And I'll talk a little bit about assignment 1. So let me turn off the light and start so the Eurotunnel is also called the Channel Tunnel or the Channel. Construction started in 1988, and it took 6 years before it was open. So these are the credits for the visuals that I used. So in terms of history, it's been a long while discussion between England and France about a permanent link, and seems to have started in the early 1800s, but at that time it was felt that it would compromise the British national security. You know, in France, 1800, Napoleon is in charge, and there had been some issues, some fighting between the UK and France, so they felt that it was not a good idea. An attempt in the late 1800s took place on the British side, but didn't work. In the early 1980s, Margaret Thatcher and François Mitterrand decided that it would happen, but with private funds. 5 different solutions were proposed, but the tunneling approach won the job, so there were bridges and tunnels, but the tunnels turned out to be less expensive, and so the tunneling approach was the one that was chosen. The project started in 1988 and opened in 1994. So here's the tunnel. There are 2 tunnels, one way, the other one coming back, and the terminals on either side. The decision was, before I go to the geology, the decision was that there would be no cars in those tunnels because of ventilation and pollution issues. So there would be only electric trains that would travel through the tunnels, and that those trains could then have cars that would go into the train. Cars and trucks would actually be loaded onto the train, and then they would be moving from one place to another. So from the geology point of view, the material at the bottom of the channel between France and England is rock. Mostly it's soft rock. You see that green layer at the surface, so you see here this is the water level, and these scales here are in meters. So the water level is at about 200, and then the green layer is a layer of chalk. So chalk has a high content of lime, and so it's a limestone type of rock. And below that layer, the darker gray layer, was a chalk marl. And the chalk marl is a material that has more clay content than the chalk. And it was felt that, well, both materials are soft rocks and are relatively convenient for drilling tunnels. That was the good news. The chalk, the lighter green zone, was fractured and probably would lead to a lot of water intake in the tunnel if the tunnel was to be drilled in the lighter green area. So they chose the chalk marl the darker green area zone, which is anywhere from, it's about 20-30 meters thick, and the tunnel would go down to a depth, if you look at this depth, it's of the order of 70 meters, 60, 70 meters, plus the 50 meters of water. You're talking about 120 meters of water pressure. So if the water would actually be coming into the tunnel, there was a lot of pressure that had to be balanced by the tunneling process. So this is what the tunnel looks like. You have tunnel going one way, and then a tunnel coming back the other way with the trains. There is a service tunnel in the middle of it. You see it right here, to service, and it also is a way for emergency exits. If one of the train, or if there's a fire or an emergency in one of the train, then the passengers can go through these connecting tunnels. I think they're about every 250 meters. So the passengers can go and access the service tunnel and escape from the tunnel. And then there is also, you can see this arching tunnel here. This is a ventilation and a pressure reducing vent, if you wish, because imagine you have a tunnel and you have a train. These are high-speed trains, so they come in at about 200 miles an hour. And when they come into the tunnel, there's a piston effect, and the air is being pushed in front of it, so it's quite a shock to the passengers. And so these ducts that go from one tunnel to the other soften the blow, if you wish, when you go into the tunnel. So this is a more detailed description. You can see here the two large train tunnels, 7.6 meter in diameter, 30 meter apart between the two tunnels, and 50 kilometers in length, about 30 miles. The service tunnel was 4.8 meters in diameter, and then the cross-passage tunnels, these are the C, designated as C here, are 3.3 meter in diameter, and they vary 375 meter spacing. The piston relief ducts are 2 meter in diameter, right here, and they're every 250 meters. So there was some other things, ventilation shafts, undersea crossovers, pumping station. So there was a lot of drilling to be done in that case. So here's a rendition of the tunnel, if you wish, underground. You see the two main tunnels here, the service tunnels, the escape tunnels, and then the ventilation ducts right here. So tunneling boring machine, there are a number of ways to make a hole in the ground, but if you have large, deep tunnels to build, then the tunneling boring machine, or TBM, are the best way to go. And you can see here huge TBM. You see the size of this person right here, so that gives you an idea of how big the TBM can be. How do they work? Well, they're very long. You certainly understand that in certainly circular tunnels are the easiest ones to drill. You have the cutter head at the front with carbide or diamond head to be able to grind the rock. And then the rock cuttings go back, and they're transported to this conveyor belt here that goes and takes the rock fragments all the way to the beginning of the tunnel. Then below that, so you have a forward shield, and then you have a tail shields. And the tail shields has those blue pads here. You see that these are gripper shoe. And these gripper shoe push sideways and press against the tunnel to provide the reaction so that the forward sheet can be extended through a telescopic shield and penetrate. And then once you have penetrated a certain distance, then you release the gripper shoe, you advance you retract the telescopic shield, and then you put your gripper shoe again, and then you progress in that fashion. You can see here, this is the operator's cabin. So the size gives you an idea of how big those things are. Also, there are two types of solution: open shield cut, where you don't have the pressure balance, and the pressure balance TBMs, where the cutter head is sealed and can prevent the water from coming into the TBM. We'll see in a minute here. And so here is an example of the tunnel boring machine being placed in the tunnel. Then once, if I go back here, right here, you have the ring beam erector. So this ring beam takes the segments of the tunnel and grabs them and puts them in place. And that's what this picture is showing you. You see those blocks. So this is what, maybe half a meter or so, or maybe even a meter thick block. That's part of the tunnel liner that's going to be placed once you have excavated the rock. You can see them coming in on the delivery train, and then here they are placed one by one and aligned, pushed sideways by those jacks. And then once you've done this, you inject grout between these segments, the lining elements, and the rock, so that you seal everything from the parent rock. So here's an example. Well, this is actually a crossover cavern. They had to have some flexibility to make the tunnels crossover. And then final breakthrough. It's amazing because you have to know where the joke is that if you get the French to start at one end and the British to start on the other end, well, they're going to end up with two tunnels because it's difficult to, I'm just kidding. But through advanced techniques, surveying techniques, engineers are able to know exactly where they are underground. And the final breakthrough, you can see here that the British and the French are getting together. They met within centimeters, a few centimeters of the target. So it's really impressive. Now, in terms of passengers, the blue line, you have number of passengers in millions on the right, on the vertical axis, and then you have the years, 1994 when it started, and then the million tons of freight. So this has been, it handles between 15 and 20 million passengers per year going in both directions. And then one last note, the total project, you see the initial estimate and the total cost. The cost overrun was about 100%, so it started around $7 billion, ended up at $14+ billion. So that, let me get the lights. So that's the Eurotunnel. Remarkable accomplishment of civil engineers. Let's go now to weight volume relationships. So when, let me write this up here. weight, volume relations. So if you have a soil, we talked about last time, you know, the particles, and if you consider, if you think of the soil, you're going to end up with a soil rock sample that has some grains in it, like so. And then you're going to have some water in the sample, so you're going to have some water here, water there. And the soil may not be completely saturated, so you may, in addition to the water, you may have some air bubbles or that exist in the soil everywhere. So there are really always three components in the soil sample: the solids, the water, and the air. Now the water could be if we have leaks, for example, we could have kerosene or things, and the air could be a gas in general. But we'll just consider water and air and solids. So you can actually reorganize this diagram in what we call the three-phase diagram. So the three-phase diagram is a rendition of this picture here, but we're going to regroup all the solids together, we're going to regroup all the water together, and we're going to regroup all the air together. So we're going to have water right here, we're going to have solids here, these are the grains, and then we're going to have air right here. Realize one thing is that the solids have no holes in it. That solid is a solid piece of rock, if you wish, because you've taken all the grains here and you sucked all the water and all the air out of it. So this piece right there is solid rock. So it's a conception, it's one way to look at things. And we're going to show on one side, and let's see, how did I set that up? It doesn't matter. So on one side, we're going to put the volumes, and on the other side, we're going to put the weights. So here, you can see that we're going to have the weight of solid, WS. We're going to have the weight of water, WW. And then the weight of air, we're going to consider that to be 0. It's because it doesn't weigh much. But it does weigh, because if you think about it, we have an atmosphere that's about 15 kilometers thick above our head. And that's air, all the way up to 15 kilometers in altitude. And that 15-kilometer column of air creates the atmospheric pressure, which is 1 ton per square foot. So you take 1 square foot of floor space, and that column of air weighs 1 ton. So it's, but we have neglected the weight of the air because it's really very small compared to the weight of water and the weight of solids. On the, we will add the total weight to this, W sub T, total weight of the sample. On the volume side, we will consider the corresponding values. So we're going to have the volume of solids, we're going to have the volume of water, and we're going to have the volume of air. Okay, we cannot neglect it. It may not weigh hardly anything, but it occupies some volume. And then this one here is going to be the volume of voids, V sub V. And of course, here we will have the total volume. So this is what we call a three-phase diagram. You have two special cases, and you have to be careful when you look at the statement of the problem. You could, the problem may start by saying a dry sample of sand. So dry in there gives you a clue because that says no water. So if the material is dry, then your diagram simplifies to something like this. You're going to have some solids, here, and you're going to have some air. Okay? That's the dry sample. And then the other case is saturated. So the material, so if it's a saturated sample of clay has a unit weight and so on, then you can start your diagram right away by saying, all right, I've got solids and I've got water. So that's, simpler. But if it doesn't say saturated or dry, you're stuck and you have to assume that you have three phases. And that's why we talk about this being a three-phase diagram. Now you can be sure that at the midterm, there's going to be a three-phase diagram problem. I mean, that's a pretty given thing. Always start your problem by drawing your three-phase diagram and then put these things, okay? Because at least I can give you some points if you do that. If you don't put anything, I can't give you partial points. So any problem that deals with a three-phase diagram, boom, draw your phase diagram, and that's always a good start. Now, from this diagram, we define the number of parameters, properties of the soil that are going to be very useful to us. And I need to go over those and define that. So the first one will be the total unit weight. So total unit weight. Okay, that's going to be gamma T. And the total unit weight will be the weight of the sample divided by the volume of the sample. So WT, over volume VT. All right. Second unit weight, dry unit weight. All right, well that's pretty simple. Dry unit weight is going to be gamma dry, or D, gamma sub D. And the dry unit weight will be just the weight of solids because we don't count the water. So it could say a saturated sample of clay has a total weight of this or volume. And what is the dry unit weight? You got to find out the weight of solids because this is going to be weight of solids divided by total volume. That's the definition, dry unit weight. And then unit weight of solids. Unit weight of solids. So the unit weight of solids is the unit weight of that chunk here. And that chunk, I told you, has no holes in it, okay? All the air has been sucked out, the water is sucked out. This is a solid piece of rock, concrete. So the unit weight is quite a bit higher than the other two. This is gamma solids, or gamma S, equals WS over VS. And if you're stuck in the desert and you have to assume a value on those things because you may be stuck in the problem, well, this is usually for mineral-based soils about 27 kilonewton per cubic meter. Total unit weight, to give you some range of possible values, I put 17 to 22 here. 17 to 22 kilonewton per cubic meter. And then dry unit weight will be less than that, and I put 14 to 18 here. 14 to 18. Okay? So that means that if you do a problem and you find dry unit weight 1.4, something's wrong. Okay? This is the typical range. Now it could be 12, it could be 19, but not 1.4. Unit weight of solids. While I'm at it, I'll put unit weight of water, because that's always a good one. Because we know that it doesn't change. Gamma W. And the real number is 9.81 kilonewton per cubic meter. But we'll, in all our calculations, so that's going to be weight of water over volume of water. And then we'll use 10 kilonewton per cubic meter to simplify our calculations. Specific gravity of solids. Specific gravity of solids. It's a fancy name to normalize. That's G sub S equals gamma S, unit weight of solids, divided by gamma W, unit weight of water. So you can see 27 divided by 10, again, 2.65, 2.7. If you're in the organic range, you can have things that go down quite a bit from this, all the way to wood, which is at 1.2 or something like that. But these are reasonable values. All right. So these are the well, we can let's do saturated unit weight. Saturated unit weight. So the saturated unit weight would be gamma sub sat. And in this case, you can see that it would be WT, W. We would have the solids, WS, plus the water, WW. And if we saturate the material, then we're going to have to fill this part here with water. And if we fill it with water, it's going to weigh volume of air times unit weight of water. Okay, and this is divided by the total volume. That's the saturated unit weight. And then let's move on to, so these are the unit weights. Let's move on to the other parameters that we use typically. First one is water content. So water content is the little w. That's the weight of water divided by the weight of solids. This is very likely to be a question on the midterm. Why? Because it's a bit surprising, if you wish. You know, if you told me what's the water content of this in this material, you would think, well, I'm going to give you the ratio of the weight of water divided by the total weight. So if you say 20% of water, then that means out of 100 grams, I'd have 20 grams of water. No, that's not the. So you have to be very careful, because to me, at least, it's not very logical. But there was good reasons for doing that, and we'll see that later. But remember then that it's the weight of water divided by the weight of solid. So it's this weight right here divided by this weight right there. It's not this divided by the total. And we typically quote this in percent, so times 100. And the range here varies from, what did I put? I mean, it varies quite a bit. In there, I put water content 10 to 40%. 10 to 40%. But you have some organic materials that have 2,000% water content. You know what to do. Well, there's the water content. What else? Degree of saturation. We use the symbol large S. And that is the volume of water divided by the volume of voids. So it's this one divided by this one. So if I say the degree of saturation is 80%, that means that 80% of the voids are filled with water. So if the material is dry, then the degree of saturation is 0 because there's no water. If the material is saturated, then 100% of the voids are filled with water, and the degree of saturation is 1. So the degree of saturation can vary from 0 to 100%. By the way, in the equations, when you have equations, you need to use the number, the ratio, not the percentage. But you know, it's a habit that we have in civil engineering to quote those things in terms of percentages. Degree of saturation, porosity. Porosity is the parameter N, and porosity is the volume of voids divided by the total volume. And it varies from 25 to 50% is what I put in there. So porosity is volume of voids, how much voids do you have, and divided by the total volume. And then the void ratio is E, volume of voids, divided by volume of solids. And we use actually the void ratio more often than the porosity. And so you have to be careful that these two definitions, volume of voids over total volume is porosity, volume of void over volume of solids is the void ratio. And so the void ratio will be typically larger. And here I have 0.4 to 1. Because it's typically, it's just habits in the practice of geotechnical engineering. Some of those numbers are quoted as percent, some of those numbers are quoted as ratio. So void ratio, and then there's also something called the density index. So I sub D, or D sub R, there are two symbols. I believe I sub D is the recommended letter by the International Society. A lot of people use D sub R. This is equal to E max minus E divided by E max minus E minimum. So it's a ratio of void ratios, and E max will be the large void ratio. So that's associated with the loosest state. This is the natural state, This is the loosest state, this is the densest state. So what you do typically, let's say you have a dry sand, picked it up on the beach, you get a dry sand and you have it in your bucket, and it has a certain void ratio. You can take the bucket and shake it, it's going to densify the sand, you're going to minimize the volume, you still have the same weight, the void ratio will decrease. If at the same time you take the same bucket and you pour it into another same bucket, but very gently, it will be in a very loose state, and the void ratio will increase. So E max is the loose state, E is the natural one. So this gives you an idea of the relative density or the density index. It's not used very commonly. But so these are now, the bad news is you need to know this by heart. Okay, these definitions are critical, and it's, you know, there's a lot of logic in it, total unit weight, dry unit weight. So remember, try to remember those things through logic. But these things, that whole series of things, the values are helpful, you don't need to memorize them. The definitions, you do need to memorize them. Okay, so having done this, let's see. Let's see if we can do some, yes, I need to cover this. So if I need, I want to keep this. Let me erase this. I told you you would have a problem on weight-volume relationships, and there is a certain sequence to follow to be sure that you can solve all those problems. So solving a weight-volume problem. Okay, one diagram of WV. So three-phase diagram. That's what we call the phase diagram. So always start by doing a phase diagram. Step 2, indicate known W's and V's. So for example, if the problem starts by saying a 1.2 cubic meter of soil weighs 2 tons, and so this, you're going to put W total is 1.2, sorry, the V total is 1.2 cubic meters, and W is going to be 2 tons. So you read the statement of the problem, and you write down you indicate 3 if dry or saturated, then you reduce your problem to a 2-phase diagram. So read carefully the statement, because the word dry and the word saturated are a mathematical input, if you wish, because it reduces the number of unknowns. Number 4, if no quantities of weight or volume are given. You say, well, wait a minute, if you don't give me the weight and volumes, I cannot solve everything. Well, sometimes the problem will read a sample of clay has a void ratio of 0.6 and a water content of 27%. And there you're not given a weight or a volume, you're just given some of those ratios. And so that's the case here. If no quantities of weight or volume are given, assume, the best way to assume a 1 cubic meter volume of solids. That's the best way to do it. You can, you don't have to do that. You can do other assumptions, but this one will lead to simpler calculations. 5, complete the diagram by finding all remaining quantities. So, for example, if you know the total weight and the total volume and maybe the weight of water, then by difference between total weight and weight of water, you can find the weight of solids. And if you have the unit weight of solids, if you know the weight of solids, boom, you can get the volume of solids. And then if you have the weight of water, you always know the unit weight of water, so you can always go from one side to the other of this one. Here you cannot do that. You have to find VA by difference between VV and VW. So that's what you do in 5. You try to complete that picture, you get an answer for all the red parameters there. And then 6, calculate all required quantities. So for example, once you have all the quantities in here, it may say, what is the water content? So then you go in here and you say weight of water over weight of solids. So you can calculate the water content. What is the porosity? Well, you say volume of voids divided by total volume. So now you can calculate all the, so let's do an example together. And we're going to do one of the problems that's on the assignment. So remember, the assignments are not required, but it's a good idea to do them. So I hope all of you will do them. And they will be graded. And if you get 90 or more on that assignment, you will get automatically 1 point additional on your final grade. So once I get all the grades, and average the labs, the midterm, the final, and you're at 89, and you've done 3 assignments, boom, you're at 92%, and you get an 8. So good idea too. And remember, you have the solutions, because all the problems come from the book, and you have a solution. So it's kind of a gift, if you wish, but don't copy. You can copy the solutions at the end, but make sure you know how to do these things, because you won't have the book in the midterm, you won't have the book in the final, so make sure you understand how to do those things. And the best way to do that is to do it by yourself first, and only if you get stuck, then you look at the solution. All right, having said this, now, assignment 1 will be due, let's see, 7 September. 7 September at 8 a.m. or before 8 a.m. You need to turn in, and you'll have to, we'll give you more details on how to upload and your assignments and so on. So let's go do problem 3.1. Where's 3.1? There's 3.1. So 3.1 says, a sample of clay is brought back from the field, extruded from the Shelby tube, and trimmed to the following dimension. Height, 150 millimeters. So, sample of clay. All right, I'll start my phase diagram. It doesn't say dry or saturated, so I'm stuck. I say, all right, I'm going to have solids, I'm going to have water, and I'm going to have air. And here I'm going to put the weights, and here I'm going to put the volumes. So W is on this side, I'm going to take that in kilonewtons, and then the volumes on this side, and I'm going to do that in cubic meters. So I have I need a line here, line there, and right away I can put 0 here for the weight of air. Volume of air, volume of water, and then total volume and so on. Alright, so I've started the diagram. It says the height is 150 millimeters, the diameter is 75 millimeters, it weighs 13.2 newtons. Alright, boom, 13.2 right there. Times 10 to the minus 3. Okay, because I want kilonewton and they gave me newton. Because I know the height and the diameter, I can calculate the total volume. Alright? So I did that and I got 6.62 10 to the minus 4 cubic meters. What else does it say? The water content has been determined to be 25%. So I know that the water content, W, is 25%. So that means that weight of water over weight of solids is equal to 0.25. What else is given? The soil donné the presence of organics. Find the following parameters. So no organics, that means that I can assume that G sub S in the definitions, so G sub S equals 2.7 or gamma solid equal 27 kilonewton per cubic meter. Okay? So then I have to define unit weight, degree of saturation, porosity, void ratio, dry unit weight, saturated, you know, all those quantities. So the we've assumed that the unit weight of solids is 27. We need to find out what the some of those quantities are. We're going to put 0 right here because we know that already. 0. And then we don't know weight of water, don't know weight of solids, but we know the ratio is 0.25. We also know that weight of water plus weight of solids, weight of water plus weight of solids is 13.2 times 10 to the minus 3 kilonewtons. So if I use this equation and this equation, I've got two equations, two unknowns. I can solve for WW and WS. When I do that, I find 2.64 10 minus 3 here, 2.64 times 10 to minus 3, and then I find WS 10.6 10 minus 3 by difference. Okay? These two add to 13.24. Okay? Now, once I have the weight of water, I can go on the other side and find the volume of water because I know that the unit weight of water is 10. So I get on the other side, I think I used 9.81 in the problem, but so that would be 2.64 times 10 to the minus 4, since there is a ratio of 10 between the two. And then, what else can I do? Well, I remember I assumed that I had gamma S equal 27. So that means I know this unit weight, so I can go from here to there. And in that case, I found 3.91 10 minus 4 here. 3.91, 10 to the minus 4. And that means 50 minutes. All right, let me just finish briefly. All right, I've got 6.62, that's the total volume. Minus this, minus that, now I can find the volume of air. And I got 2.48, 10 to the minus 6. 2.48 times 10 to the minus 6. So not much air. Now that all this is filled, then I can calculate all the things that are required, which are natural unit weight, this divided by that, the degree of saturation, the weight of water divided by the sum of those two, volume of voids, porosity, volume of voids divided by total volume, void ratio, volume of voids divided by volume of solids, dry unit weight, weight of solids divided by total volume, and saturated unit weight. I've got to transform this into weight of water, and then recalculate the total weight divided by the total volume. Okay, so that's an example, typical problem of what you're going to face in the midterm. All right, I will see you next time.